All right. So are you ready to see the world in like a totally new light? I mean, literally today, we're going deep into the physics of light. How it moves, how it bends, bounces around, and basically like how we can see anything at all. Our source material for this deep dive. We've got Chapter 9 from a physics textbook. It's all about ray optics and optical instruments.
It's pretty amazing how much we just take light for granted. You know? I mean, flip a switch, boom, there it is. But the science behind it, that's fascinating.
For sure. Okay, so the book starts off talking about light traveling in straight lines.
Right.
But then it also says light is a wave. Isn't that kind of contradictory?
It does seem like one of those paradox things, but it actually makes sense once you dig deeper.
Okay.
Think about shadows.
Yeah.
They exist because light, generally does travel in straight lines.
Right.
If it was curving all over, we wouldn't get those crisp outlines.
Yeah, that's a good point. But it's also a wave.
Right. Light has this dual nature.
Yeah.
It acts like both a wave and a particle. The reason we usually see it acting like it's going in straight lines is because the wavelength is teeny tiny compared to the stuff we see around us.
Okay.
Yeah.
So for this deep dive, we're focusing on the ray aspect of light.
Exactly.
Kind of like a simplification to help us wrap our heads around it, right?
It's like using a map to get around a city.
Right.
You don't need every little detail, just the main streets and landmarks.
Okay, that makes sense. So thinking of light as a ray helps us understand things like reflection.
Right.
Which is what happens when light hits a mirror.
Mm-hmm.
But mirrors seem pretty straightforward. You see yourself, what's so deep about that?
Well, have you ever noticed how some mirrors, like those funhouse ones,
Oh, yeah.
make you look all stretched out or squished?
Oh.
Or how the passenger side mirror in a car says objects in mirror are closer than they appear?
Yeah.
That's where things get interesting.
Okay, I'm intrigued. So the textbook talks about different types of mirrors, like concave and convex and a bunch of terms like focal point and all that.
So those funhouse mirrors, the ones that distort your reflection,
Yeah.
those are curved mirrors, either concave or convex.
Okay.
And the way they're curved dictates how they reflect light,
Okay.
which is what creates those wacky distortions.
And what about that car mirror example?
That's a convex mirror. The outward curve gives you a wider field of view,
Okay.
but it also makes the reflected image smaller.
Okay.
That's why things appear farther away than they are safety first, but also a cool physics trick.
Whoa, so there's actually a lot more to mirrors than meets the eye, so to speak.
Definitely. And this is where the textbook's discussion of the mirror equation and magnification comes in.
Okay.
These tools help us predict exactly where an image will appear in a mirror and how big or small it will be, all based on the mirror's shape and the object's location.
Wait, so if I know the type of mirror and where I'm standing,
Yeah.
I can calculate exactly where my reflection will appear and how distorted it'll be.
Precisely.
Nice.
You could even figure out how to design a mirror that makes you look twice as tall.
Oh, why
Or turns your reflection upside down.
That's wild. Now I'm really seeing mirrors in a whole new light.
And we haven't even touched on refraction yet.
Oh, no.
That's where things get even more mind-bending, as we'll
Oh.
see in the next part of our deep dive.
Okay, so we've talked about light traveling in those straight lines
Mm-hmm.
and then how it bounces off mirrors.
Yeah.
But the textbook also mentions this thing called refraction, which is when light bends as it passes from one medium to another,
Right.
like from air to water. I've definitely experienced that.
Yeah.
When you're looking at a straw in a glass of water,
Uh-huh.
it looks all broken at the surface.
Exactly. That's a classic example of refraction.
Yeah.
It all comes down to the fact that light travels at different speeds in different materials.
Oh.
When it goes from a faster medium, like air,
Okay.
into a slower one, like water,
Mm-hmm.
it bends toward a line we call the normal. Yeah. Basically just an imaginary line perpendicular to the surface.
Okay.
Yeah.
So the straw looks broken
Right.
because the light rays coming from the part that's underwater
Yeah.
are bending as they enter the air,
Uh-huh.
making our brains think the straw is in a different position than it actually is.
Right. And it's not just about air and water. Anytime light passes between materials with different densities, it bends.
Oh.
That's why eyeglasses work.
Oh, yeah.
The lenses are carefully shaped to bend incoming light rays
Okay.
in a way that corrects vision problems.
Wow.
Yeah.
So refraction is actually responsible for us being able to see clearly with glasses.
Yeah.
Pretty cool. The textbook also mentioned something called Snell's law,
Right.
which has to do with the angles of the light rays,
Uh-huh.
and something called the refractive index.
Yes, Snell's law is basically a mathematical way of describing how much the light bends,
Okay.
depending on the angle it hits the surface and the refractive indices of the two materials. The refractive index is a number that tells you how much slower light travels in a material
Okay.
compared to like a vacuum.
So a higher refractive index means light slows down more.
Yeah.
That's interesting. I wonder, is there a way to actually see this difference in speed?
Well, directly measuring the speed of light is tricky,
Yeah.
but there are some clever experiments that demonstrate how light slows down in denser materials.
Okay.
And actually, there's this mind-blowing phenomenon related to this called total internal reflection.
Total internal reflection.
Yeah.
What's that all about?
So imagine you're shining a light from underwater up towards the surface.
Okay.
As the angle of the light gets steeper and steeper,
Mm-hmm.
there comes a point where the light doesn't actually leave the water at all. It gets totally reflected back in.
Wait, so the light bounces back in even though it's hitting the surface?
Yeah.
That's crazy. Why does that happen?
It happens because when light tries to go from a slower medium to a faster one,
Mm-hmm.
at a steep enough angle, it can't bend enough to escape. So it gets trapped inside the denser material.
So it's kind of like if you were running really fast
Yeah,
and tried to make a sharp turn, you might skid out and stay on the same track.
that's a great analogy. And this phenomenon, total internal reflection, is what makes fiber optic cables work.
Fiber optics, those
Mhm.
things that bring us super fast internet.
Exactly. Fiber optic cables are basically thin strands of glass or plastic
Okay.
designed to trap light inside through total internal reflection.
Hmm.
Light signals bounce back and forth inside the cable as they travel, allowing for incredibly fast data transmission over long distances.
That's amazing. So all those like cat videos and online gaming sessions I enjoy are thanks to light getting trapped inside a cable.
Pretty much, yeah.
Who knew physics could be so entertaining?
Right.
Okay, so we've covered reflection and refraction. What else does the textbook delve into?
Well, it goes on to discuss lenses,
Okay.
which are basically pieces of transparent material like glass that are shaped to converge or diverge light.
Lenses, like in eyeglasses and cameras.
Exactly. Lenses use refraction to bend light in specific ways.
Okay.
A converging lens, like the one in a magnifying glass, is thicker in the middle
Okay.
and brings light rays together, while a diverging lens is thinner in the middle and spreads them apart.
So the shape of the lens determines whether it magnifies things
Yeah,
or makes them look smaller.
precisely. And the amount of magnification or reduction is determined by the lens's focal length.
A focal length.
Yeah, remember that term from our discussion of mirrors?
Right.
It's the distance from the lens to the point where parallel rays of light converge after passing through it.
Okay.
Yeah,
So a shorter focal length means a more powerful lens.
exactly. That's why the lens in a magnifying glass,
Mm-hmm.
which needs to make things look much bigger, has a very short focal length.
This is making me think about all sorts of things.
Uh-huh.
Like, how do camera lenses work?
Yeah.
Do they use converging or diverging lenses?
Well, camera lenses are actually a combination of several lenses working together
Oh.
to focus light onto the sensor and create a sharp image.
Oh, wow.
And depending on the type of lens, they can use both converging and diverging elements to achieve different effects.
Wow, that's way more complex than I thought.
Yeah.
So it's all about carefully shaping and combining lenses
Right.
to manipulate light in just the right way.
Precisely. And the textbook goes even deeper into this,
Okay.
discussing the lens maker's formula, which is a way to calculate the focal length of a lens based on its shape and the refractive index of the material.
Okay, I'm sensing a pattern here.
Uh-huh.
Light mirrors lenses. It seems like everything in optics comes down to geometry and math.
You're absolutely right. The way light behaves can be described and predicted with incredible precision using mathematical formulas.
Wow.
It's one of the things that makes optics such a fascinating and elegant field of study.
Speaking of fascinating, the textbook also mentions microscopes and telescopes. Those have to be some of the most incredible inventions ever, right?
Definitely.
They let us see things that are either too small or too far away for our eyes to perceive.
Absolutely. And they both rely on the principles of optics we've been discussing.
Right.
We'll dive into those amazing instruments in the next part of our deep dive.
Okay. All right, so we've explored how light travels and bounces and bends, and we've even touched on how lenses can be used to magnify things or correct vision.
Yeah.
Now the textbook dives into something called dispersion.
Uh-huh.
And I gotta admit, the name alone sounds pretty cool.
Dispersion is definitely one of the most visually stunning phenomena in optics.
Yeah.
It's all about how white light,
Mm-hmm.
which seems so pure and simple, is actually made up of a whole spectrum of colors.
Wait, so you're saying that, like, every time I turn on a light,
Yeah.
I'm actually seeing a rainbow all mixed together.
Exactly. And we can actually like separate those colors out using a prism.
Prisms.
Yeah.
Like those triangular pieces of glass you see in science labs.
Yeah.
What do they do?
A prism is basically a tool for splitting white light into its component colors.
Oh, okay.
It works because different colors of light bend at slightly different angles when they pass through the
Right.
prism. Remember refraction.
Right. We talked about how light bends when it goes from one medium to another, like from air to water.
Well, the same thing happens inside a prism.
Okay.
As white light enters the prism, the different colors get bent by slightly different amounts depending on their wavelengths.
Wavelengths.
Yeah, that's the distance between the peaks of a wave.
Right, right.
And each color of light has a different wavelength.
Okay.
Red light has the longest wavelength, and violet light has the shortest.
So the shorter the wavelength, the more the light bends.
Precisely.
Right.
Because they bend differently,
Uh-huh.
the colors spread out, creating that beautiful rainbow effect we call a spectrum.
Okay, so that's why we see a rainbow after a rainstorm.
Exactly.
The raindrops act like tiny prisms, splitting the sunlight into its component colors.
Yeah.
That's incredible. It's like nature's own light show.
It truly is. And the amazing thing is we can actually use this phenomenon of dispersion
Yeah.
to study the properties of light and matter
Oh, wow.
by analyzing the spectrum of light emitted or absorbed by a substance. Scientists can identify what it's made of, kind of like a fingerprint.
Wow. So by splitting light apart, we can actually learn about the composition of things.
Yeah.
That's mind-blowing.
It is, and there are so many practical applications of this knowledge.
Like what?
Well, astronomers use spectroscopy,
Okay.
which is the study of these light spectra to determine the composition of stars and planets.
Wow.
Chemists use it to analyze chemicals and identify unknown substances.
This is making me realize that light is way more than just something that lets us see.
Yeah.
It's like a carrier of information, a tool for exploration,
Right.
a source of endless fascination.
You've hit the nail on the head. Light truly is one of the most fundamental and fascinating aspects of our universe.
Well, I have to say, this deep dive into the science of light has been truly illuminating.
I'm glad.
I feel like I've gained a whole new appreciation for something I used to take for granted.
That's great to hear. And remember, there's always more to discover. Keep exploring, keep asking questions, and keep your eyes open to the wonders of light all around you.
Thanks for joining us on this deep dive into the science of light. We hope you've enjoyed the journey.